But I want to answer this question by telling you a true story. And that is, on July 4th, 1997, bacteria from the planet Earth first landed on Mars. They came unarmed and peacefully. They were, in fact, all asleep. Unfortunately, most died a horrible death by the Martian UV rays. However, there were some survivors. They remain hidden in their spacecraft, dormant, waiting for better conditions. Eventually, in about 1,000 years, they also will be killed by accumulated galactic cosmic rays. So the point of this story, true story, is that we have already invaded Mars. We've contaminated Mars. Now you may say, well, this is the end, that's it. Or you could say this is the beginning. And that story, of course, is Pathfinder. Pathfinder was the first spacecraft to go to Mars, officially not sterilized. Remember, Viking was sterilized, both Vikings, and all the spacecraft that were launched in the Viking era were officially sterilized, just as Viking was officially sterilized. After Viking, COSPAR, that sets the rules, decided that the surface of Mars was unsuitable for growth from life from Earth, and therefore we didn't need to sterilize spacecraft. So we have already contaminated Mars. This is an important point. Spirit and Rover each had 100,000 bacteria on them. That sounds like a lot of bacteria, but that's pretty clean. It's cleaner than the dishes in my kitchen. Right? They were clean, but that's still a lot of bacteria. Phoenix was not sterilized except its arm. Its arm was sterilized because it went down and dug into the ice. Right? We know where all these pieces are. Any bacteria that were released from the heat from the spacecraft are dead by the UV light. That was part of the story. They're killed by the Martian UV. Mars has an incredible biocidal UV radiation. The Martian environment is not suitable for any growth of life on Earth. Contamination only survives when it's shielded. So anything inside the spacecraft is still alive, it's still dormant, it's still viable. It's not growing, but it's viable. Anything released is killed instantly. So in a sense, it's contamination of a different type than we're used to when we think of contamination on Earth. And I want to illustrate this difference because it's a very important difference, and eventually I will answer your question, Al. This seems like a long-winded answer, but this is all important background to understanding the answer to your question. Imagine you had rabbits, 2 sets of rabbits, and you took one set to Australia, continent that starts with A, you're going through the alphabet. You took another set to Antarctica, another continent that starts with A, and you released them. And then 10 years later, you decided you didn't want to do that, it was a bad idea, and you're going to decontaminate them. Well, in Australia, that decontamination would be exponentially hard because, in fact, that experiment was done. And the Australians are struggling mightily to get rid of the rabbits. Right? And it is exponentially difficult, essentially impossible. In Antarctica, you would find 2 dead rabbits not far from where you left them. The reason is that Antarctica is not a place where rabbits can grow. It would still be expensive to go get those dead rabbits, right? But it would be linearly expensive. The cost of decontamination is linear with the cost of the contamination itself. And I'm going to call this biologically reversible contamination. This is biologically irreversible contamination. This is biologically reversible. It is not a adjective that describes the size of the contamination. It's an adjective that describes how difficult it is to undo it compared to the cost of doing it. Is it exponentially hard or linearly hard? On Earth, we always think of biological contamination as exponentially hard because most environments on Earth are suitable for life. Mars is not. Let's go to biologically reversible exploration. The idea is to change the basis of planetary detection from preserving science to biological reversibility. It doesn't have much change for current robotic missions. You can still send them contaminated, but you keep track of where everyone is. And if sometime in the future you decide you want to hit the Control-Z button, you want to undo the contamination, you can still do that. And so I'm arguing that the robotic and human exploration of Mars should be done in a way that is biologically reversible. We must be able to undo our contamination of Mars if we discover a second genesis of life. Now, here's an example of something you wouldn't do. This is, you're on Mars, you're commanding your spacecraft, and it says, are you sure you want to drill into this subsurface Martian aquifer? You cannot undo this action. Right? Isn't it wonderful when your computer warns you? We need to extend that metaphor into space. Certain things you would not do, like drill deeply into an underwater aquifer, because if you contaminated that, that would spread exponentially. And to go to your question, this is reversible. This is contamination, but it's reversible. Everything you're doing is left on the surface. These humans are venting organisms from the back of their life support system. Those organisms are being killed by the UV. The organisms inside the containers are still alive. They're there. It's reversible, and it would be costly to clean it up, but the cost is linear, not exponential. So that's my long-winded answer to the question of how do you rationalize a search for life, a search for second genesis, with humans, which are arguably the best tool to do that search, and yet they're a dirty tool. The answer is you don't just give up, you work that tool in a careful way so that you don't do anything that's irreversible.